Hello class, this is Dr. E again. Today we're going to begin a very important chapter. A chapter about an extremely important concept, that of energy. Energy is a very complicated topic, and we'll see that it has many different aspects that actually makes it difficult to explain. It's like a lot of things. We know it when we see it. We also talk about energy a lot. You probably say the word energy many times during the day. High energy, low energy. I'm about out of energy. Let's get an energy drink. Mental energy, emotional energy, positive energy, negative energy. Or you might, if perhaps, talk about different sources of energy. Nuclear energy, solar energy, geothermal energy. You might talk about kinetic energy, potential energy. I know maybe you don't talk about those that often, but we will in this lesson. You're likely to talk about conserving energy, alternative energy sources, sustainable energy, energy efficiency. I'm not lazy, I'm just in energy saving mode. So in this chapter, we're going to talk about a lot of topics related to energy. Our lead slide has three important statements about energy that will hopefully help us understand what we're talking about. One, energy is needed to do work. We'll cover that in the next slide. Energy can exist in many forms, and these forms are interchangeable. One definition of energy is that it is a property that can be transferred from one object to another. Another important concept about energy is that the total energy in an isolated system is conserved. Those terms have a lot of meaning, which we will explain as we go into different lectures. So let's begin with a fairly standard definition of energy. Energy is the ability to do work. Isn't that great? You have a definition that involves another term that you have to then define. What is work? Well, work is defined as the force times displacement. That is, work W is equal to F, force, times displacement, D. And that probably helps you a lot, right? Work is force times displacement. So what does that mean? Well, the standard or most obvious explanation for what we mean by work being a force times the displacement is moving an object against gravity, such as our fellow pushing this boulder up a hill. He's moving a mass against the force of gravity. So that's a fairly obvious definition of work. But there are many other types of work. If we compress a spring, we are actually performing work. I was looking around the house to see if I could find a spring, and I happened across my garden shears. You'll notice a spring. I can compress the spring. That is actually doing work to compress the spring, and it takes energy to do work. If I release this, it springs apart. So energy is the ability to do work such as compressing a spring or compressing a gas in a container. Other types of work involve moving charged species against an electric field. I know that's a little complicated. Moving substances against their concentration gradient. No, that's also a little complicated. Converting one chemical substance to a less stable chemical substance. Yeah, that's a little bit complicated too. But my point is there are other types of work in addition to work against the force of gravity. But let's stay with our example of lifting a weight, moving a weight against the force of gravity, because it is very illustrative. This is what we call mechanical work. The important equations again are work is equal to a force times a displacement. And from the last set of lectures on classical physics, you know that the force of gravity is equal to the gravitational constant G times the mass of an object. Force is equal to mass times the gravitational constant. On the right, we see our friend lifting a weight, doing his workout. And he's lifting a 110.2 pound weight above his head, and that is lifting it to a distance of 6.56 feet above the ground. Now, why these numbers? 110.2 pounds. Well, probably many of you could lift a 110 pound weight above your head. And 6.56 feet would be about the distance that you would be lifting it above the ground, most of you being about that height. But I picked this weight and height to go through a step to convert dimensions into more scientific units, CGS units. So let's take our 110.2 pounds. If you remember from one of the previous lectures, we gave some examples of how we can interconvert units. And in this case, we want to go from pounds to kilograms. And we will see here that if I multiply 110.2 pounds times this factor of 1 kilogram is equal to 2.046 pounds, setting this up so that the pounds will cancel, I can then convert 110.2 pounds to 50 kilograms. Or in other words, 110.2 pound weight is equal to 50 kilograms. Similarly, 6.56 feet. Let's convert that to meters, a more scientific way of expressing this height. There is a relationship that 1 meter is equal to 3.28 feet. Okay, so setting this up in this way, I can cancel the feet. Multiplying this 6.56 by this ratio of 1 divided by 3.28 leads to 2 meters. Or in other words, my 110.2 weight and a height of 6.56 feet is really 50 kilograms raised to a height of 2 meters against the force of gravity. Okay, so I have 50 and 2. Actually easier numbers, but now numbers in CGS units that we use in science. But let's convert this force, going back to one of our equations above, force is equal to mass times gravity. Well, if the mass is 50 kilograms and the gravitational acceleration constant is 9.8 meters per second squared, multiplying these two out, I get 490 kilograms times meters divided by second squared. That's a mouthful. Well, it turns out that kilograms times meters divided by second squared, since that is a mouthful, we define that as what is called a Newton. Kilogram meters per second squared is a Newton. So in this case, the gravitational force felt by this 50-pound weight is 490 newtons. That's the force. Newtons is a measure of force. The work needed to lift this 50-kilogram mass 6.56 or 2 meters from the ground, that work is equal to the force that we just calculated above times the displacement, which is 2 meters. That is 490 kilogram meters per second squared, or 490 newtons, times 2 meters, the displacement. Multiplying these two together, I get 980 Newton meters. Newton meters. Now, Newton meter is also a little complicated to say, and so there's another unit of measure called a joule. Joule is actually a measure of energy, getting back to the topic of this lecture. So, in other words, to lift a 50-pound mass 2 meters above your head takes 980 joules of energy. Now, 980 is close to 1,000. So you could say it takes almost 1,000 joules or 1 kilojoule of energy to lift this mass or this weight 2 meters above the floor. So I give you this example so you have some idea of what a kilojoule of energy is. A kilojoule of energy is the energy required to lift a 50 kilogram weight or 110 pound weight 2 meters or 6.56 feet above the ground. That is when we're doing our exercises in the gym. Each time we lift that 110.2 weight above our heads to a height of about 6.56 feet, or a 50 kilogram mass to a height of 2 meters, requires an energy output of about 1 kilojoule. Now, where did this joule come from, this measure of energy called a joule? Actually, it was named after an Englishman named James Prescott Joule. He was an English physicist, really an amateur scientist, and his primary income was by being a brewer. So on the side, he did some physics experiments that studied the relationship of heat and what he called mechanical work. shown on the right is the device that he used in some of the experiments in which he showed the relationship between what he called mechanical work and heat. And his research helped lay the foundations for the law of conservation of energy and the first law of thermodynamics. And we'll get to the first law of thermodynamics and the concept of conservation of energy in the next lecture or two. On the bottom are shown several symbols. These are really equations that show the interrelationship between energy in joules, that's J on the left, and other units of measure or other concepts. You see the Newton meters. P, this is Pascal. This is a measure of pressure, and this is a measure of volume. This is watt seconds, and C would be charge in coulombs times voltage. This is to support the point I made earlier that there can be different types of energy. There can be electrical energy, there can be pressure volume energy, and it's not just the displacement of a mass against the force of gravity. That's the only type of work for which energy is required. Energy shows up in other kind of phenomena. Okay, we're going to pause, have a brief quiz, and when we come back, we'll talk about potential energy and kinetic energy and power, some other concepts related to energy. See you in a while.